तुम तो मत कपड़े का तो मत ही बोल, हम देखें एक ही रेड कलर का फ्रॉक था। तो ऐसा तो मत ही बोल, कुछ नहीं कर रहा था।
Okay, so in this case, it seems like this should follow for any n, right? But that's not the case. Uh, Actually, this quantity itself. I can hear some sound. I don't know why I hear some sound. Okay. Uh, Maybe this comes in. Let me think if this is okay or not. But temperature should not be a function of. Actually, this will not come. Okay, if I try to, let me see if I try to jump ahead. mm, it's something that we have to jump ahead to actually show this. So let's not jump ahead of this. But essentially, I'll tell you what this n has to be equal to one, and only then can we say that if u is a function of t, then PV has to be equal to RT. Otherwise, the dependence there will be some dependence on V or P or something like that. So T can alone not be dependent. Uh, there has to be a linear dependence of PV on T. Okay, so that is important. Okay, so that is one thing. Again, for to show that, we'll have to go to chapter 12 to do that exercise. Clearly, I tried tried to see if we can actually without invoking more advanced equations prove it, but clearly that does not work here. So again, so going back, so the important thing which I wanted to show here was that PV by RT actually comes from this fact that in the low velocity limit, sorry, no low specific volume limit, you actually kind of get this fact that PV by RT tends as in totally to one. So that is very important thing. Compressibility tends to one, very away from as a dry gas is always an ideal gas. Okay, if you're dry enough. So that is what I wanted to say. Okay, now the fact why van der Waal equation was such a breakthrough I'm trying to claim. Okay, uh, and the answer is it was first of its kind cubic equation of state. The first cubic equation of state. And to understand that, to actually understand that, we will have to kind of go to see how the T plots look like for an ideal gas. Okay. How do PT plots look for an ideal gas? So how do they look? They look something like this. They will look something like this. These are hyperbolas, right? Right? What is our x and y? Let's say x and y is p comma t or p comma v. Yeah, that's better. P and v. These are different isotherms. Now our statement is that this kind of fails near the saturation dome. So near the saturation dome, if you go closer, this thing fails. Now what happens in the near the saturation dome? So let's look what happens near the saturation dome. Near the saturation dome, this is important thing. So it might not be clear to you, but for someone who has gone and seen and looked at isotherms on our PV plot, this is how it looks like. Uh, Something like this. So let me. So in the saturated region, what we kind of see is that this line is a convex curve. This is convex. Okay, let me write that. And in this part, it is kind of concave. Okay. What do I mean by concave and convex? This is positive. This one is negative. Yeah. And then there is a transition that happens. Uh, just for the sake of my benefit, just for my benefit, let me draw this line which kind of joins these two curves. See, in this two inside the dome, things are not very what do you say? We don't want to say what is going on. Although this is a straight line, we know that. But just for my benefit, let's say we don't know what is going on inside the dome, and we are kind of saying that once the gas is left to the dome, it has a convex what do you say shape, and right to it, it has a concave shape. Do we know of do we know any functional form which possesses a property that its form towards the left is convex and then towards the right is concave. And I asked a simple question. Let me type this. Do we know of any simple functional form to represent this behavior of a, a curve changing its shape from convex in the left to concave in the right? Okay, and just so that you might not think that I'm making these things up, let me show you some real figures to back my claim. Okay, let me quickly show that part also. It's somewhere here. Right. See. So it's somewhere here, okay? So one important thing which I forgot was these are isotherms, okay? We need to kind of note that. So these are real isotherms, okay? This one. What you see here are real isotherms, and this is for nitrogen, okay? Let me paste this. So what you see is that this kind of has this behavior, and for you say for ideal gases or for regions which do not touch saturation dome, this thing does not follow. Uh, so for this yx equals to 1, right? What happens here? What is going on here? What is dy by dx? Dy by dx is minus 1 by x. And then what is d square y by dx square is 2 by x square, right? It's always positive. That is an important thing. So these lines, this behavior of convex to concave is only happening for lines which touch the concave, which touch the saturation dome. So you can see the critical isotherm. At that point, you don't have that feature. At that point, you don't have that feature. Okay, that is an important thing. That feature is lost. Okay, uh, that does not happen. Okay, so it is always what do you say convex. Wait, let me think. Yeah, it's for them. It's always convex. Convex is this. Concave is this. So what we can see is that for domes which for isotherms which won't touch the saturation dome will have all convex shape, right? This is a convex curve, right? Now coming back to the question, if we want to capture this feature that isotherms are convex in the subcooled region and then becomes concave in the superheated region, do we have do we have a what do you say? Do we have Do we have a functional form to represent this? And probably a simple one, a very simple one, a simplest one, okay? The simplest one. So let's what do you say? Let's rely on the polynomial forms. Does y equals to x has this feature? No, right? Y equals to x. This convex. It's neither convex. It's not concave. It's a straight line. It's these values are zero. Okay. What happens about y equals to x square? We know that there is a root at x equals to zero, so we can kind of say that it's a midpoint of this curve. On the right hand side, it's convex. On the left hand side, it's concave, convex. Same convex, convex. So again, this thing kind of does not follow. But what about y equals to x cubed? How does that look? And let me not plot y equals to minus x cube, but plot y equals to minus x cube. How would that look? Would that not look like this? These are the two lines. Uh, Something like this. Convex, concave. And so one important thing which people realized very early, and see this is specific volume. This is P. So what people realized very early was that if we want to mimic the behavior happening, at least not inside the dome, but near the dome, what we need to do is write a cubic equation when expressing pressure in terms of specific volume. Okay, in general. See, there is another important thing to note here. Cubic, see, y equals to x square. How many roots does y equals to x square has? How many roots can y equals to x have? Uh, or a linear function can have. This one can have one root, right? This one can have one root. This one can have two roots. Precisely what we are looking for. We need two roots also. To some equation, some kind of, we have two equations, right? So two roots we need, not two equations. We need two roots here. What does y equals to minus x cube gives you? It also gives you three roots, right? It gives you an extra root. Do we need that third root? No, right? Now, here is my proposition. You have this PV plot, right? And you have a cubic equation. Now, I will not simply assert to minus x cube, but ax cube plus bx square minus cx square minus cx plus d will roughly look like this, right? For a particular, let's say, uh, y equals to p set, we have three roots, right? This one, and this one. My proposition is, let's keep this root, let's keep this root, and let's cancel this one and say this is my VF, this is my VG. This equation, this construct has the property of convex curve to my right, to my left of my VF, concave to my right of my VG, and this I'll kind of delete. I will not treat the region between these two, kind of neglect it. And this seems to be an uh, ad hoc approach, kind of forcing this, right? X cube gives you three roots. It does not give you two roots, kind of forcing it. But still, we are kind of trying to. So we are not essentially after the roots themselves, right? We're not essentially after the roots themselves. But an important feature which x square cannot give you is the variation in the slopes or the what do you say, second derivatives of isotherms. It's only the cubic equation that can give you. And so what you will notice, no matter uh, no matter where you are, whatever how what equation you're using, what equation of state you're using, majority of them will be cubic equation of states. So they turned out to be very successful. That is what I'm trying to say. They turned out to be very successful. And the first cubic of equation of state was van der Waals equation of state. So he kind of started an entire uh, can of like models, gas models, to be able to write property variations near saturation domes. Okay, so there are all kinds of, and these are all cubic equations of state, right? So when you try to solve something like p equals to p sat, you have three roots. What do you do of the third root or the middle root? The, the ad hoc thing to do is we kind of neglect that. We don't deal with it. And to be honest, let me talk to you about it. It's not that a cubic root will always have three roots, right? It might have only one root, right? Or it has to have uh, three roots. Yeah, because the condition is that you have to either have one real root or three real roots, right? You cannot have two real roots and just go with it, right? That is not possible. So that is one thing, right? So we essentially what we do is we neglect this third root or the middle root. Okay, and why do we do this? There is also a physical reason behind why do we do that. Okay, there is a reason behind it. Definitely, our equation of this cubic equation of state will definite is not capable of modeling anything inside the dome. Okay, that is something that we are very upfront admitting. But at least outside the dome and near the saturation lines, can we attempt to model our gas using this cubic equation of state? Yes, we can, because it has the properties that we require. Okay. Okay, so that was the first thing which was excellent about van der Waals equation of state. Um, do I have something else to show to you guys? Um, right, one more thing. Yes, indeed. One important thing to note is that uh, you can actually use the critical property. See, uh, this entire property of, see, as I mentioned, right? As I mentioned, let's note this here. Okay, if I draw a y equals to constant line in this region, you note that you get two solutions, right? Two for a single isotherm, you get two solutions. But above the dome, you get a single solution. If we kind of am neglecting the third root, this is the exact feature that cubic equations of state also offer. Either you will have two roots, or let's say either you will have three roots or one root, which suggests that our equation of state is also capable of uh, predicting what is happening near the critical point. Okay, so that was also an important thing that we noticed. And actually, van der Waals kind of derived, could actually calculate the values of his coefficients A and B. So I've been using the notation A and B, but A and B are van der Waals constants. He actually derived these based on the critical properties of the gas. So let's do that. Okay. Actually, as I was mentioning to you guys, this concave and convexity of the thing. See, at the critical point, to the right of the critical point, del square P by del V square is negative, positive. But on the, so on the right it is negative, but on the left it is positive, which dictates that at the critical point, this should be a zero. So actually, this is a very well-known fact that uh, what do you say? Yeah, it's a very well-known fact that critical point is an inflection point. Another important thing to note is at this point, it kind of touches, it does not cross the saturation dome. So at this is the point at which Vf equals to Vg, right? So this also dictates that the slope of the isotherm dp by dv should also be zero. using these two conditions and applying it to the van der Waals equation of state, we can actually uh, substitute A and B to get our what do you say, critical property. So I'll just quickly show that to you, and then maybe we can close for today. We'll do the problems, whatever problems you would like to do. If you're available, you guys are there. Next time we will solve some problems. So just let me show this part to you, and then we'll close. Okay. So P plus A by V square P minus D is RT. Okay. Now I write P equals to RT by V minus D plus minus A by V square. So now what is dP by dV? dP by dV. I'm not writing T, or let me write this so that. So I'm saying T equals to constant, then maybe let me write this. So T equals to constant. Uh, Let me write T critical. Then this will become dP by dV will become RT critical there will be a minus sign, right? This will be plus 2A by V cube. Okay. The second equation, as I said, is over the inflection point. Minus 6A by V to the power 4. Both these terms, or both these expressions should be 0 to calculate, for us to calculate V critical. First of all, we'll calculate V critical and then substitute this thing back to the equation of state to get P critical. So that is something that we need to do. Okay. Just simultaneously solving these equations, I get RT critical by V minus B square. Or let me write 2RT critical V minus B Q is equals to 6A. So basically 3 by V, okay, is 3 by V times 2A by VQ, isn't it? Now what is 2A by VQ? It's minus, it's RT critical. This is also, so I'll substitute V, I'll calculate for V and later on do this. This is V minus B square, okay? V minus B square, cancelling to both on both sides. What do you get? You will get 2V critical, or 2V equals to 3V minus 3B. Is this all right? Yeah. So then you get V equals to 3B. 3B. This is V critical, okay? We are solving for V critical. So note that. Now, okay. So we have solved for V critical. Now I also need to solve for T critical, okay? So I know my V from V critical. let me also I could quickly calculate A from V from these either of these two equations if I know my P critical also, or let me represent all critical properties in terms of A and B. Let me do that, okay? Instead of finding A and B in terms of critical properties, let me find critical properties um in terms of A and B, okay? So now in that case, uh, because you know that RT critical is V critical minus B is V critical into this thing. Now, what is V critical minus B is 2B, right? 2B to the power square. This is 3B minus B is 2B, 4B square. 4B square. Uh, and V critical cube is 8B cube. No, wait. Um, Not 8B cube, 27B cube, 3B square, no? So this you get, T critical you get as 8A by 27B R. And then just simply substitute whatever there is to get P critical. So P critical is RT critical divided by 2B minus A by 39B square, right? So now you substitute RT critical as 8A by 27. So this becomes 4A by 27B square. Now this is 3A by 27B square. So you get this to be equal to A by 27B square. Okay. Now what am I trying to say here? That A and B are two quantities. P critical, V critical, right? If you know P critical, V critical, and you have an equation of state, you can quickly find what the values of A and B. So what you essentially need is the critical point to find A and B. Okay. There is a microscopical or statistical picture to A and B. I will not go into that, but uh, essentially another important thing to note, which can be actually which gets very quickly explained by van der Waal equation of state is that let me non-dimensionalize this equation with its critical property. So P by P critical is your P star. So this becomes P critical. V star, and this is V critical square. This is V star V critical. And then RT critical is T star T critical. Okay. Now let's start substituting things. Okay. You see A by B. So this becomes 9B square, right? 9B square. A by 9B square. What is this? This is A by 27B square. Right? This is B critical is 3B. So 3B. What is this T critical? T critical is 8A by 27 RB. So R, now see how R gets cancelled. So the dependence on the molecule species, right? If it is an oxygen or something, gets quickly cancelled out because R gets cancelled, right? Now, this B you can take common. So this becomes 3V star, okay? 3V star minus 1. You have taken a B common, so you you multiply it in the here, and now you take A by B square common here, okay? A by 9v square you take common. A by 9v square. This is P star by 3, I think. You have taken common as A by v square, and this is 9v square, okay? So now if I cross the common terms, what I have is there will be 8 is fine, 8 will remain. There will be a 3, 8 by, this will be 8 by 3. Let me also take 1 by 3 common. So essentially you will have 3. So this will become P star. And this 8, it only remains 8, T star remains. Okay. So essentially what I'll be writing here, um, I'm writing 8 T star divided by 3V star minus 1 minus 3 by V star square, isn't it? And what is this? This is P star. Okay. Let me do one more thing. Let me divide this. Let me find out compressibility, which is Z PV by RT, right? PV by RT. Now, let me do this one more thing. P star V star divided by T star. Oh, sorry. This you will get 8 3 minus 1 by V star, isn't it? Minus 3 by V star. This is the equation which I kind of showed to you when I was discussing this at one point. Here. This is essentially principles of corresponding state. So it kind of explains to you why, upon reducing the pressure and temperature in terms of their with respect to their critical values, why all gases must behave roughly ideally. Kind of tells you that Z is a function of reduced pressure, and I can just quickly substitute V in terms of P and T, and at different uh, reduced temperatures and very reduced pressures, this is what I will get. This is what is there, okay? If you want to see this, should we see this? We have some time. Let's try to see this. Let me just first see if I have done this correctly. So T star I have to take common. So T star was not here. I have to have T star here also. Right? And then V star you take common, so you get this. Okay, this is fine. Let me quickly show it to you. So let's say our T star is 1. So T star is 1, and I'm wearing P star, so P star becomes X, okay? Now I need to plot y. What is my v 1 by v star? So 1 by v star is something that I need to find. Okay, so this is a little problematic because this is a cubic equation in V. So finding solutions to that has to be done graphically or numerically. But rest assured, we can do this. This can be taken up as an exercise to see that if I vary my P star and calculate my Z star, my compressibility factor Z, this is what I should get. And this is independent of your, this is independent of your gas composition or gas molecules, right? This is principle of corresponding states. Van der Waals equation of state leads you to the principle of corresponding state, which was unexplained by ideal gas equation of state. And it does a lot of more things. I didn't even go into I didn't even touch the tip of the iceberg. It was a gold mine, a simple two-factor correction in the equation of state led to so many, what do you say, no, so many, so much analysis, which I have not even discussed yet. And that was the interesting part about about van der Waals equation of state. Another important thing which I just quickly checked is what is the critical uh, compressibility value? It's actually 3 by 8. What is 3 by 8? What is 3 by 8? So if you put in all the values P critical into V critical by T critical, you will get the value as 8 by 3 by 8. What is 3 by 8? 3 by 8 is 0.375. Van der Waals equation of state says that your critical compressibility factor should be 3 by 8. For sure, this is a high value. The compressibility factors there are much, much lower. But anyways, it is able to predict a non-unity compressibility factors close to critical point or close to saturation domes. I didn't go into the depths of what this what essentially is done with the third root and so on with the cubic equation and so on, and it explains a lot of things. It even explains metastable states. So this third root is kind of hints you at what do you say, the metastable states. I didn't talk about it. Probably we don't need to talk about it too much. We have already gone too much away from the general discussion of the video lectures. But I took this time because not a lot of people had joined today. I took this class as a detour to just show it to you that there is so much that we are not discussing. And this is just a tip of iceberg that we are discussing in this video lectures. I hope this was an interesting discussion that I carried out today. Um, let's meet next week. Let us solve some problems. Unless there are people in the video lecture in like live, there are people in live. It becomes quite the questions could be done quickly, and there is no feedback element when solving these problems. So this was an issue, and that is why I didn't solve problems. Uh, so that is why next time let's meet and let's solve some problems. So nice to record this session. Nice to yeah. Please enjoy the lectures and all the best.